Howdy, we're Team French Press. This is our final presentation on Project 5. To launch an attack, the victim must be running operations that are secret dependent, such as AES table lookup. The attacker leverages shared resources, such as lastable cache in the figure. In this project, each person independently implemented one attack. The efficacy of our attacks is also verified through experiments. In Permanent Probe, the attacker occupies a set, waits for the victim to evict his data, and then measures the timing. The RDTSP instruction is crucial for timing measurement, and POSIX thread is for multi-threading. The attack is tested with Gen 5 simulation. The system configuration is laid out in the table at the bottom. In experiment, we started from a simple scenario and move on to a more realistic one. In the single-threaded scenario, the secret bits are randomly generated. Depending on the secret bit, the victim may do nothing or evict a line. This is similar to square and multiply algorithm. As you can see on the left, the attacker guesses the key bit on the fly. On the right side is the Gen 5 output. We're able to achieve 100% accuracy. And these are the key bits and guesses made by the attacker. In the multi-threaded scenario, for simplicity, the victim operates on interleaving bits. On the left is the program, where you can see the victim doing key-dependent operation. On the right side are the key guesses. The attacker retrieved 95 bits out of 100. Most lost bits happen at the beginning. In the first case, 100% accuracy may sound unbelievable, but it makes sense considering the benefits from the natural serialization and the low interference from other processes on a simulator. In the second scenario, we start to witness key bit losses because of a lack of synchronization, but it only means the attacker needs to take more samples. Now, Mark will take over and present Flush and Flush.
Flush works by measuring the latency of a cache line flush to determine whether a memory region has been accessed recently. Since it doesn't make any memory accesses, it's fast and stealthy. This diagram visualizes the principle of the attack. Cache line flushes usually have fairly consistent latency. If populated, a cache line will take longer to flush. Therefore, reads and writes can be detected by measuring the time taken to flush a cache line. The application of this attack is shown in the following demo. A victim program will count the occurrences of each character in the input. In this demo, the 10,000 most common passwords are used as input. From a different thread, the attacker program will use these memory accesses to attempt to reconstruct the input. Each entry in the output is then measured according to the number of wrong characters it has, including extras and missing characters. While it's running in the terminal, we have a previous output on the left, and the victim and attacker are shown on the right. The rest of the code is on the GitHub, linked later. In the output, notice that many strings are correct, but some characters are wrongfully added or missed, including some of the new lines. Now let's see the numbers. The attack is generally successful. The left diagram shows how many passwords had a given number of flaws. The right diagram shows the same info as a proportion of a whole. As we saw, a large majority of passwords either had no flaws or were still easily recognized because of how few there were. This shows that the attack works even from another thread, with no synchronization necessary. It also demonstrates that the input data can be stolen with fair accuracy, even if the input is never cached. Naturally, since this attack was run straight on a machine, the main barrier to its accuracy in this case was the non-deterministic environment it was run in. Next, Farabi will show off his flush reload attack.
For flush and reload attack, the attacker first invalidates all the cache sets using CLFlush instruction and then allows the victim to access one of the locations which is used for secret. At the third stage or the reload stage, the attacker then again accesses all the locations of the cache. However, he or she will have only the secret location as cache hit. All the other locations will be missed since it were invalidated previously. We have implemented flush and reload attack in two environments. In Gen 5 microarchitectural simulator environment, we have 100% accuracy since we could control all the parameters of the architecture, and in a real machine of Intel 10700K processor, we had 97% accuracy. In conclusion, if we go through all the attacks, we will see that shared resources in general are a security concern. If we have a key dependent execution, then we need to handle it with care. And the closer we get to real execution, the harder it becomes to retrieve the secret bits. And if we compare between all three attacks, we can see that prime and probe is more generalizable since it does not depend on any sort of special instructions. However, it's a bit slower than the other two attacks, and flush and flush is the fastest one. Thank you everyone for watching. We're Team French Press.